Okay, sorry for being late. Okay, last time, we discussed about this orthogonal complement. So complement is something like this, a complement in the context of a set. Okay. Okay, so so let's see or let's study what it means in the context of subspaces. Okay. Okay, so again, when thinking about this orthogonal complement, we were thinking of this. So we start with some maybe five-dimensional entire space, and then we consider some subspace W, okay, and of course this is closed under linear combination. Then you consider some vector x, and then such that this vector is orthogonal to this subspace W, right? But this thing, I mean, we have to think about the orthogonality or like a perpendicularity between two vectors, not between a vector and the subspace. So this means, or the fact that x is orthogonal to the subspace W means that you pick up any vector, for example, small w. So this is a vector, okay? And so any vector w, you have to satisfy this, okay? So if you can guarantee x is orthogonal to any vector that you pick up from your subspace, and in this case, x is orthogonal to subspace W, and let's think about how. Let's think about the way to satisfy this this condition, because usually in our subspace W contains infinitely many different vectors. So W contains infinitely many different vectors, and so we cannot check if this vector x is orthogonal to all these W vectors, right? So one quick way or one easy way to check if this condition or this condition is satisfied is as follows. So if you have a subspace W, and then this subspace will be basically in the form of a span of some vectors, right? So suppose your your subspace W is a span of maybe three vectors, v1, v2, v3. Okay, and then so let me use new page. Okay, so v1, v2, v3. Okay, and then if x is orthogonal to the subspace W, and then it means x is orthogonal to v1, and x is orthogonal to v2, and x is orthogonal to v3. Okay, if you satisfy these three, then x is orthogonal to any vector in subspace W. And let's see why. It is very simple. So in this subspace, suppose you picked up any vector, maybe small w, and this small w can be represented as a linear combination of these three vectors, right? And then let's think about the inner product between this x and w, and then this x times or x inner product c1, v1, c2, v2, c3, v3, right? So far so good. And so here we apply a distributive law. So this is x transpose and the same thing, and then it is c1 times x transpose v1. plus C2 times X2 X transpose V2 C3 X transpose V3, right? So if X was orthogonal to V1, V2, and V3, and then it means X transpose V1 equals 0, or X inner product with V1. So each component here will become 0, right? So if you linearly combine zeros, then it will be equal to always 0, right? So basically, if you can show your vector x is orthogonal to those basis vector that spans your subspace, and then that's enough, or that's sufficient, that x is orthogonal to any vector in the subspace W. Okay? So that is this guy. A vector x, is orthogonal to W, and then this x should be orthogonal to every vector in a set that spans W. So it means if W is span of V1, V2, V3, and then if x is orthogonal to every vector in this set that spans your subspace W, so here we only have a 3 vector, right? So each of these 3 vectors are orthogonal to your vector x, and then x is orthogonal to your subspace. Okay? And then what was this guy? W, we call this as a W perpendicular. And then this is another subspace, and so if you collect all these vector x such that this vector x is satisfying or orthogonal to this subspace W, so basically you collect all the vector x that satisfies this this condition, and then that set of vectors, all the possible vector x, is called this W perpendicular. Okay, so this is a another subset of the vectors. Okay, another vector subset, and then each vector is satisfying this equation. And also, more importantly, this W perpendicular is also not just a vector subset, but it's also a vector subspace, which means if you collected all these vector x, and then these vector x's are also closed under linear combination. Okay, closed under linear combination. So let's see, let's prove that. Okay, so suppose x, your subspace W is spanned by these 3 vectors, and then, so if you want to show the fact that this subspace is closed under linear combination, you have to pick up the 2 vector, and then let's suppose that vector was x and y. Okay, so these are the randomly chosen 2 vector from W perpendicular, and then by the definition or the condition that this x and y has to satisfy, x should satisfy these, right? And then also y should satisfy these. So y is perpendicular to V1, V2, and V3, right? Okay, then let's think about their linear combination. Maybe a1 x plus a2 y. So a1 and a2 are just 2 scalar values that forms this linear combination. Okay, and then we have to check if this vector, let's call this vector as z, which is a linear combination of x and y, and then we have to check whether z is perpendicular to W. If this is satisfied, and then W is also belonging to W perpendicular. Okay, so that way we can show that this W perpendicular is closed under linear combination. And okay, let's check if this is true. Okay, so in this case, so a1x plus a2y. So this vector, let's think about its inner product with v1. And in this case, it's a1 times x transpose v1 and plus a2 times x2 x transpose y transpose v1, right? So each of these inner product should be 0, right? Because x and y each was belonging to your W perpendicular. Okay, so in this case, z is also perpendicular to v1, and also likewise z is also perpendicular to v2 and v3, and so z is perpendicular or orthogonal to the subspace W, and so W, we can obtain the conclusion that W is also belonging to your subspace W perpendicular, which means W perpendicular is closed under linear combination, and thus W perpendicular is also a subspace. Okay. Then let's move on to this theorem 3. And this is a quite important part. It's a really important part. So yeah, please pay attention to this theorem 3. So now using this subspace W and also its orthogonal complement, which is W perpendicular. So by the way, this W perpendicular is called the orthogonal complement of W. Okay, and so if your subspace was some column space of some matrix A, okay, so we now consider the matrix A and then its column space and null space and things like that. And you guys know column space and null space is also a kind of subspace which is closed under linear combination, right? And then we now think about, given this particular subspace using matrix A, what is this orthogonal complement of this given subspace of column space of an A? So initially you are given a matrix A, and then think about the column space of an A, okay? And then what is its orthogonal complement? Okay? And then orthogonal complement is actually equal to this guy, which means you first think about the A transpose, okay? So let's think about this example, V1, V2, V3. Then let's see. Suppose your matrix A was 1, 2, 3, 4. Suppose this was your matrix A, and this was V1, V2, and V3. And then the column space A is this guy, right? And then this orthogonal complement of this column space of A is actually equal to this guy, which means we first form A transpose, which means we have a V1 transpose, V2 transpose, V3 transpose. Okay, and then the null space of this matrix, is actually the same as this guy. Okay, and then what was the null space? So the null space was all the vector x that satisfies this 0 vector. Okay? Okay, now let's try to understand why this is true. Okay, so in this case, let's think about the first element in this matrix vector multiplication. How can we represent this first element? This first element will be the inner product between this and this, right? And so it can be written as V1 transpose X, right? What about the second entry? Is V2 transpose X and V3 transpose X, right? And then this has to be equal to 0, 0, 0, this three-dimensional vector, right? And so this is a homogeneous linear system. So in this case, we considered it as a kind of vector equation. So in this matrix A transpose, we kind of considered these 1, 2, 3. Maybe we may have more. Maybe 1, 2, 3, 4, 5. And then this X was 5-dimensional vector, right? And then we considered it as a linear combination of these 5 columns. Okay, so that's our understanding from the previous chapter. But now we think about the matrix A row by row. So in this case, this first element is just inner product between this row and our vector x. Okay, and that should be 0. And this guy also should be 0, and this guy should be 0, right? And so it gives you x transpose v1 and x is orthogonal to v1, v2, v3. Okay? So this guy was actually the condition that we have to satisfy in order for this vector x to be perpendicular or orthogonal to your subspace W. Okay? So if x satisfies this, and then this x is belonging to the perpendicular or orthogonal complement of this column space of an A. Okay? So that's why we obtain this equation. So again, you think about the orthogonal complement of this column space of A, and then you first just transpose the matrix A, okay, and then consider its null space. That will become your orthogonal complement of column space of an A. Okay. Okay, then similarly, we can think about this row space. Although it's first time to study or hear about this row space, but it's just similar to column space. So column space was all the linear combinations of your columns of matrix A, and then in this row space, it will be just all the combinations of rows of matrix A. Okay. Okay. Okay, in this case, so if you have maybe 4 rows in the matrix A, and then think about the subspace W, which is a span of, so this is a V1 transpose, V2 transpose, V3, V4 transpose, and then it will be those 4 vectors, the span of these 4 vectors, right? And then if your matrix was A was this, and then we have to transpose it, A transpose, right? So that way Oh, sorry. In this case, if you think about the row space of matrix A, and then these are the basis vectors of your subspace, and then each column should be orthogonal to your vector x. So in this case, you just multiply A times x and then set it as 0, which means row space of an A and its orthogonal complement, it is the same as null space of A. Because just multiplying A times x equals 0, and then it will be just like giving V1 transpose x, V2 transpose x, and 2 more, and then set this vector as 0. Right? Okay. So you understand this as well. Yeah. Hmm? Which one?
Isn't it the same? I mean, for null A and null A.
Okay, so null A transpose is, so let's think, yeah, let's first consider null of an A. What is this? So it is all vector x that satisfies Ax equals 0, which is this homogeneous linear system. And then what about this A transpose? You just replace this matrix A as A transpose, right? So it is just, yeah, you can simply understand it this way. So the basis is our column of matrix A, and then you have to form the inner product between this column and your vector x. And so in order to form the inner product, you have to first transpose or make one of the column vectors into row vector, and that's why we do the transpose. Okay, any questions? Okay, then that's it for the first chapter, chapter 1. Then let's move on to the second chapter, which is called orthogonal set. Okay, orthogonal set is basically a vector set. It's a set of vector in a particular universe. So if you consider R5, and then maybe you obtain 3 vectors from this R5, and then let's call that as U1 and U2 and U3. And then you consider this set of vectors, and then if this set is an orthogonal set, and then it has to satisfy for each pair of these vectors, each of them should be orthogonal, or their inner product should be 0. Okay, so for I and j, which is whatever you picked up, if you consider or compute this inner product, it should be always 0. Okay, so this kind of case, right? So among, if you consider these are 3 vectors, and then if you pick up any of the 2, these two, they will be always orthogonal to each other, right? So this is one good example of orthogonal set. Okay, and also if you remember what we learned last time, if they are, if this vector set is orthogonal, and then they will be automatically linearly independent, right? So this is the next theorem that we see here. So orthogonal set is automatically linearly independent set. Okay, so yeah, this is a kind of our intuition that we discussed last time. So basically, orthogonality is a much more strict condition than linear independence, right? So if the linear independence would be just be satisfied if the angle is just non-zero between the two vectors, right? But as I mentioned last time, they should be maximally linearly independent, which means their angle should be like a maximal, which is a 90 degree. Okay. Okay. So this, so far this is our kind of intuitive understanding about it. But let's try to formally prove it. Okay. So yeah, the proof is quite simple. So how do we prove this? How do we prove these vectors are linearly independent? Then we go back to the definition of linear independence or dependence. So we basically form this vector equation and then set it as 0. So this 0 is actually a vector, right? So this is a homogeneous linear system in the form of a vector equation. And in this case, if the solution is if the only solution, if the solution is always the trivial solution, so if you cannot find any other solution, and then we can conclude that these are linearly independent, right? Okay, then let's try to just compute or solve for C1 through CP. So even though we don't even know what our vectors are, U1 through UP. We don't even know the details of these vectors, but all we know about these vectors are they are just orthogonal to each other. Okay, we just utilize that fact so that we can obtain the conclusion that we only have a trivial solution. Okay, so the trick that we're going to use is simple. So from this vector equation, we just multiply the vector u1 and u2. And we just not multiply this, but we consider the inner product. So if this vector and this vector are the same, and then of course the same vector with the inner product of 0, and then u1 with the inner product of c1, u1 all the way through cp, up, right? Because this 0 vector is the same as this guy, right? Okay, then this right hand side is this, right? And then the left hand side will always give you 0 because the inner product with the 0 vector will give you 0, right? Okay, then let's apply this distributive law, and then this guy will be distributed into this manner, in this manner, and so we will obtain this, and then this, right? And then the key point here is this part is composed of the inner product between this u1 and the other vector in our set, right? So u2 inner product with the u1 and the inner product between up and u1 are all 0 from the requirement of this orthogonal set, right? And this guy, the inner product with itself, okay, u1 and this u1. And let me ask this. So first of all, is this a scalar or a vector, or even a matrix? So it's the inner product between the same vector. The inner product is what? Vector or scalar? It's a silly question. It's a scalar, right? Okay, and then let me ask the second question. Is this scalar non-zero or 0? It should be non-zero because it means the length of this particular vector. And what if this vector was initially just a 0 vector? In this case, Okay, so I don't know why, but we are excluding the zero vector when considering the orthogonal set. Okay, because zero vector doesn't make sense, right? So in this case, the orthogonal set will be just a trivial. So we just exclude the zero vector in our orthogonal set. In this case, the length of this vector u1 will be non-zero. So we can safely divide each part by this scalar, and so it will lead us to the fact that this C1 becomes 0. Okay, and then we multiply, or we do the inner product on this equation by using U2, and then likewise we will obtain C2 equals 0. Okay, so that way all the C's, C1 through CP, should all be 0, and so we can show that all of these linear combination coefficients should be 0, which means the trivial solution will exist. Only the trivial solution will exist, and so these U1 through UP are linearly independent. Okay, and then now, since we are discussing about this homogeneous linear system, and then now let's move on to some non-homogeneous linear system. So what if we have some non-zero vector in the place of this zero vector? Okay, so these ones are forming some linearly independent set. Okay, and then now let's think about some vector y. Okay, that is belonging to the span of u1 through up. Okay, so it is so one example is as follows. So suppose we have two vectors that are orthogonal to each other. So these two vectors are your orthogonal set, and then since they are also linearly independent, they will form, or we can consider the span of these two vectors as this kind of plane. And then you pick up one vector from or inside of this span of these two vectors. Okay, and in that case, we can represent that vector as a linear combination of these two basis vectors that we have, right? And then what will be the linear combination coefficient, okay, to represent this vector by using these two basis vector that we have. Okay, so that is the question that we want to solve in this slide. Okay, so we first picked up this vector y from the span of these vectors. Okay, then this y should be, if we think about the vector equation, it will be C1 U1, C2 U2, and CP UP, which is the linear combination of those basis vectors U1 through UP. Okay, then what is this C1 through CP? Okay, how can we solve this? Okay, one typical way would be just forming, so suppose y was 1, 2, 3, and then u1 was maybe 1, 2, 5, and then 2, 3, 1, and then maybe the third vector was -1, 2, 0. And then this is just a typical linear system that we have to solve. And then what we would do is just this, forming this coefficient matrix, and then this given vector 1, 2, 3, and then we would convert it to reduced echelon form in order to obtain the solution. But if your vectors are orthogonal to each other, and then the C1, C2, CP can be actually obtained quite easily. So this is really the beauty of orthogonal sets. So let me show you how. Okay, so the trick is quite simple. So in order to obtain the C1, okay, so this is our given equation. So in a vector equation form, right? So y and u1 and up, and then they are orthogonal to each other. And then we just simply multiply or compute the inner product with this and u1, for example. And then this guy, inner product with u1. Although this guy should be put on the left side of this, right? But you guys know u inner product with v will be the same as u inner product with v inner product with u, right? So we can conveniently write it in this manner. Okay, and then the trick is exactly the same that we saw in the previous slide. We just distribute the inner product, and then what about these parts? These parts will be composed of u2 inner product with u1 through up inner product with u1, which will become all 0. They are becoming all 0, right? And so if we rewrite it, then the right hand side will become u1 inner product with y, and then the right hand side will become c1 times u1 u1. So this is just a multiplication, and then these are the inner product with the same vector itself. Okay, and again this guy is a constant, right? So this guy is a constant because it's just an inner product, and so we can simply divide it from each side, and then this c1, okay, c1 will become like a u1 inner product with the u1, okay. So y and u1 inner product between y and u1 divided by u1 inner product with the u1, okay. So so that way we don't actually need to solve the linear system, okay. So let me see if we have the inner product. Yeah, so suppose y was this, and then your orthogonal set was, yeah, this was u1, and then suppose u2 was maybe 1 and what? So let's try to obtain the orthogonal vector to u1. What should be the value corresponding to this place? So we want to form the orthogonal set of u1 and u2 by expanding or slightly modifying this example. Okay, so suppose u1 was this 4, 2, and then what will be u2? That is another vector in this orthogonal set. Minus 8. So we have to satisfy this. u1 inner product with the u2 should be 0, and then 4 times 1. So 4 and 2 times x becomes 0, right? X is minus 2, right? So we have a 4, 2 as one vector, and then 1, minus 2 is orthogonal vector to u1, right? And so now we can form this yeah, this orthogonal set. Okay, and then now let's assume that, so let's assume that y was picked up from the span of these two vectors. Okay, and then the question is, question is 7 comma 6 should be represented as C1 times 4 comma 2 plus C2 times 1 comma minus 2. And how do you obtain C1 and C2? Huh? 40 over 20, yeah, right. Over 20, yeah. Okay, so here, yeah, so you understood this, right? So we just you applied this equation in order to obtain this C1, right? And then, yeah, one really interesting characteristic is that in order to obtain C1, was U2 involved? So the question is, does other vectors like C2 or C3 and so on, do they affect C1? It's not at all, right? In order to obtain C1, you will only use this U1, right? And also, of course, this Y vector as well, right? But other vectors in your basis doesn't affect the coefficients of this C1, okay? So that way, they are not really like an entangled linear system. So if your vectors are orthogonal to each other, and then you can really simply obtain or compute the linear combination coefficient of C1, C2, and so on by just using the corresponding single vector, just one vector. Using just one vector, you can really easily obtain these linear combination coefficients. Okay? So that way, you don't even need to form augmented matrix and then do this reduced echelon form kind of things. Okay? So yeah, you guys know how painful it is to compute RREF or reduced echelon form, but in this case of orthogonal set, you don't need to compute this reduced echelon form. It can be really simply solved or easily solved. Okay, then now we move on to quite important but intuitively quite simple concept of this orthogonal projection. Okay, orthogonal projection. Okay. So orthogonal projection is something like this. So yeah, so you first consider some subspace W. Okay, some subspace W, and then your subspace W is actually span of some orthogonal vectors. Okay, so this is a starting point. Again, you are given a subspace, and then you have the basis vectors that are orthogonal to each other. Okay, that is the starting point. And then, so one example would be this. So let's start with maybe R3. So in this entire space of an R3, so we have these two orthogonal basis vectors, and then the span of it. And then you consider now some vector that is not necessarily inside of this span. So you pick up any vector in this three-dimensional space, and then in general this vector is like will probably be outside of this really thin plane, right? So you pick up any vector that is not necessarily inside of this vector. Okay, and then now what you want to do, or here in this slide, our task is to decompose this vector as some vector inside of this subspace, and then another vector which is not kind of inside of this this subspace, but here one condition that we have to satisfy. So it is something like this. So we are suppose we have maybe 3, 4 as one single point, and then your subspace was spanned by this single vector. Okay, so this vector was 2, 1. Okay, so you pick up one point in R2, okay, and then you have the subspace spanned by this single vector 2, 1. Okay, by default, if you have just one vector, you can kind of conveniently say this vector as orthogonal set. Okay, and so now we have this span. And then here, let's decompose this vector as the summation of the two vectors, and then this vector can be decomposed into these two vectors, right? So suppose this vector was y, okay, and then this first vector was maybe v1, and the second vector was v2, and then y will become v1 plus v2, right? This is a kind of one decomposition, or just another representation as the summation of the two vectors for this given vector y. Or it gets dirty, but you can decompose this vector maybe like this vector and this vector. So this one can become another v1 and v2, and then also it can be represented as this green v1 and v2 and their summation, right? And now here, considering this subspace W, okay, so we consider a special case of a decomposition where the first vector is belonging to the given subspace, okay, and then the second vector is belonging to W perpendicular. Okay, so this is a main story of orthogonal projection. Okay, so okay, it's a little bit small, so let me rewrite it. So we considered maybe 3, 4 here, and then 2, 1, and then we consider this subspace, right? And then this vector can be decomposed. Okay, so this vector y becomes, yeah, maybe v1 plus v2, and then again I mentioned that v1 should be belonging to the subspace W, which means this v1 should be along this line, right? So let's call this as v1. Okay, and then there can be many different vectors along this subspace. So let's just randomly choose one vector. So suppose this guy was v1. Okay, and then what will be the v2? v2 will be this, right? So this one will become v2, right? This is one kind of a decomposition. Or let's think about the other, some other case. So you now use much shorter v1 as something like this, okay? And then your v2 will become this, right? So in both of these cases, we are satisfying this, right? Because v1 was along this line, but we add additional constraint or requirement so that this v2 should be belonging to this W perpendicular, which means v2 should be orthogonal to any vector W such that W belongs to our subspace W. Okay, and then intuitively that vector will become this this is V1, and this is V2, and V2 and V1 are orthogonal to each other. Okay, so we want to obtain this particular decomposition. Okay, so that V1 belongs to the initial or original subspace, and then V2, okay, which is the remaining part in this decomposition of vector y. This remaining part should be belonging to the orthogonal complement. Okay, and then let's obtain such V1 and V2 by using these requirements or these conditions. Okay, then first of all, V1 can be represented. So by the fact that V1 belongs to this subspace W, and here in this particular case, W is spanned by okay, let me change the notation. Okay, let me change the notation following the book's notation. So this V1, the book is using the notation for V1 as this y hat. Okay, so something like this, and then another remaining part as a z. Okay, so this one is V1 and this one is V2. Okay, okay, then this one will become y. And then suppose W was span of, for example, V1, for example. Yeah, so here, please do not get confused. So V1 here is something like this, 2, 1, which will form our basis vector for the subspace. Okay, and then how can we represent this y hat? It should be the linear combination of the basis vectors of this subspace W, right? And so y can be represented as alpha times V1, right? So we are discussing this special case of our subspace being just one-dimensional or spanned by this single basis vector. Okay, okay. And then now we have to satisfy this. V2 should be perpendicular to our subspace W. How can we represent that? Okay, so here in this case, z can be represented as y minus y hat, right? Which means y minus alpha times V1. Okay, so yeah, let me change the notation slightly because we are using the orthogonal basis. So let's call our basis vector as u1. Okay, then here it will become u1. Okay, and then now z should be u1, right? Because you pick up one vector from the subspace W, and then one of the basis vector can be just one vector that was picked up from your subspace, right? And so we at least have this satisfy this, right? Okay, and then let's just rewrite it. So z is this. So y minus alpha times u1 times u1, right? And this should be 0, right? And so y times u1 equals alpha times u1 times u1. And so alpha should be this, right? Okay, so we suddenly got the exact same answer from the previous one, right? But here, if you think about the situation here, So the situation is, so we are given some subspace, and then we have the orthogonal basis for that subspace. Okay, and then given a particular vector y that is outside of the subspace, we want to decompose this vector into as the summation of the two vectors, where one is completely inside of our span, and the remaining vector is also completely orthogonal to your subspace stuff. Okay, in that case, this component, okay, this component can be obtained by using this linear combination coefficient, okay, by for our basis vectors, okay, and then this vector will become the orthogonal to any vectors in your subspace. Okay, and then in this case, the geometric understanding is again this. So you want to decompose this vector as one belonging to your subspace and then the other having the 90-degree angle. And in this relationship, let's see, this vector, okay, so this vector is called, so we call this vector as orthogonal projection of this vector, the original vector. Okay, so this original vector is projected. Okay, so we have some kind of sun or some kind of a light source, and then light source are shedding the lights, and then the direction of the light is orthogonal to your subspace. Okay, so basically the direction of this light, I mean the vector of this light direction is not visible from your subspace. It will be just becoming just a single point. Okay, it will not be like this kind of slanted, or it doesn't have a slope, right? So that is the meaning of the orthogonal projection. So you shed the light orthogonally to your subspace. Okay, and then that shadow, the shadow vector, is your orthogonal projection. Okay, and that vector will become this black vector, and then we call that as y hat. So again, y hat is called orthogonal projection of y onto u, or equivalently span of u. Okay, if we have just one single basis vector as u, and then this c is called the component of y, which is orthogonal to u, or the span of u. Okay, so again, we decomposed one vector into two different components, where these two components are added to form your original vector. And one component is completely inside of the span, and then the other one is completely orthogonal to your subspace. So this C is called the second component, okay? One of the two components of the original vector y that is orthogonal to your subspace stuff. And this has a special notation of this projection of L of projection onto the subspace L of y. Okay, so here L is the subspace. Okay, subspace L, and the subspace will have some orthogonal basis vectors, right? And this projected component, orthogonal projection of some vector y, will become this. Okay, okay, then now okay, then let's move on. The next thing is about the ortho. Yeah, it starts with this ortho, but it has a different second term of normal. So orthonormal sets. Okay, so in this chapter we studied orthogonal set. Now we study orthonormal set. So orthonormal set is quite simple one. I mean, slightly changed version of orthogonal set. So so this is one example of an orthogonal set where two vectors are perpendicular to each other. So at this point they are orthogonal set, but not yet orthonormal set. But if we want to change them into orthonormal set, we don't change the direction of these vectors, but we only change the length of the vector so that the length of each vector becomes 1. Okay, so I briefly mentioned about this. So we change or scale the vectors by either stretching or shrinking along the same direction of each vector so that the length of each vector to be 1. Okay, so if you change your orthogonal vector set in this manner, and then the resulting vector set will become orthonormal set. Okay. And here, the simplest example of this orthonormal set is this standard basis. So what was the standard basis? Okay, so in the maybe 5-dimensional space, okay, one more. Okay, so if you consider these 5 vectors and consider the set of these 5 vectors, they are one example of orthonormal set, because are they orthogonal to each other? So you pick up any pair and then compute the inner product. The inner product will become always 0, right? And then, are they having the length of 1? Are their lengths always 1? Yes, right? So they have the length of 1. Okay, so let me change this example in this manner. Is this orthogonal set? Is this orthogonal set? Yes or no? It is orthogonal set. Why? The direction didn't change, right? So we simply change it or stretch it one vector 3 times, right? The length of one vector by 3 times. So the length is no longer be 1, but their direction, each pair will always be like orthogonal. Or if you compute the inner product, it will still be computed as 0, right? Okay. And now let me ask one question. Another question of this. So I just simply discarded these 2 vectors, and then consider the set of these 3 vectors. Are they orthogonal set? Are they orthogonal set? Yes. Are they also normal set? Yes or no? Are they also normal? Huh? Yeah, so still each vector has the length of 1, right? And then each pair is orthogonal to each other, right? So this is another set of orthonormal set, right? Okay, then let me ask another question, because you guys answered quite well. Oh. So we consider these 3 vectors. We initially had this 5 vector, and then we considered maybe the vector of the 3 vectors only, right? And then now let's think about adding one vector, another vector, and then consider this 6th vector. So this vector is also 5-dimensional vector. Okay. So in this case, are these orthogonal set? Are these orthogonal set? are these orthogonal sets?
There will be free variables.
Huh? Yeah, right. There will be free variable. Yeah, right. That's the correct answer. And also, you can, yeah, we can also understand it in this manner. So, orthogonal set is, as I mentioned, the orthogonal set is much more strict condition than the linearly independent one. So, as we saw in the previous example, if your set is orthogonal, and then your set will be automatically be linearly independent, right? And so, in this case, if we have a 6 vector in the 5-dimensional space, and then if we form the matrix of 5 by 6, and then as the student mentioned, we will always have at least one free variable, which means this matrix can never be linearly independent, right? And so, this one can never be orthogonal. So they are not gonna be linearly independent. They are always linearly dependent. So, yeah, it can never be orthogonal. Okay. And then this is one example of an orthonormal basis, which is a much which has a much complex form, right? So it's not just the standard vectors. Okay, and then we have 3 more slides that is quite interesting. Okay, so from here, in this kind of shape of this matrix, if your matrix, so now we think about the orthonormal basis or orthonormal vector set, okay? And then that vector set, I mean, if we just make them as one matrix, then this matrix can be this tall and skinny. It is possible, which means like in 5-dimensional space, we can have like 3 vectors that are also orthonormal, but we cannot have this, maybe 4 by 6. In this case, by looking at the shape of this matrix, we can just immediately say that they should have a free variable, and thus they are not linearly independent, and so they are not orthonormal or orthogonal, right? And so, if your vector set is orthogonal or orthonormal, and then if we form the matrix, then it should have this kind of skinny form, right? So your matrix should be really tall and skinny. Or it can, of course, square matrix. It can be square matrix, right? Okay, having that in mind, let's look at this theorem. So we have m by n matrix U, and this matrix U has orthonormal column, which means these vectors are orthonormal, having the length of 1, and then they are orthogonal to each other. In this case, if we think about this matrix multiplication of U transpose of U and U, okay, U transpose and U, and then it will become this identity matrix. Okay, so if we consider maybe 5 by 3 matrix, and then what is the size of this identity matrix? Would it be 5 by 5 or 3 by 3? So let's think about the transpose of the matrix A. And then that matrix will be something like this, right? 3 by 5. So this one will be U transpose and U, right? And so it will become identity matrix. I mean the 3 by 3 identity matrix. I mean, we didn't prove that it should be identity matrix, but at least the size of matrix of this product of these 2 matrices should be 3 by 3, which follows the smaller dimensions. Okay. Then now, let's just quickly prove that. So this guy is a U1 and U2 and U3, and this guy is U1 transpose, U2 transpose, and U3 transpose. And so this is something like this. And this, right? And then how can we obtain this? We just multiply, we compute the inner product with this and this, becoming this and this and this. So in this case, it will be inner product of this guy and the second guy, right? And so it is equal to the inner product between two different orthogonal vectors, right? So between different vectors, it will become 0. And between the same vectors, it should be 1, because we define the length of this vector as 1, because we started from orthonormal basis, right? And so, yeah, if your matrix is orthonormal matrix, and then U transpose U will become identity matrix, which has a smaller dimensions among the m by n. Okay, that's it for today's lecture. Okay, thank you very much.
혹시 줬어?
안 보였어.
그리고 저희 범위가 대체 어떻게 되죠?
네?
저희 2차 고사 범위가
아, 이제 오세요?
네, 지금 그럼 6단원도 들어가는 건가요?
네.
6단원 진도 나가야 될 거죠? 2단원, 3단원 그리고 6단원 진도.
직교 사용 저희가 이제 어떤 벡터에다가 이렇게 사용시키는 거는 얘 하나가 벡터가 있기 때문에
네네.
쉬울 것 같은데 이 상태에서 하나의 벡터를 사용시킨다 할 때는 여기서 얘와 방향이 같은 거를 찾아야 되거든요.
그렇죠.
그거는 어떻게 찾나요?
아, 그게 그러니까 그게 좋은 질문이고, 그게 아마 다음 시간에 좀 배울 것 같은데, 이게 우리의 이제 서브스페이스고, 만약에 뭐 여기가 원점이에요. 뭐 이런 벡터가 있어요. 이게 이제 사용이 되면 이제 여기가 이제 수직인 이런 걸로 나오잖아요. 그 요 벡터에서 요 성분을 어떻게 구하냐는 거죠. 근데 요 벡터는 또 어떻게 이제 분해가 되냐 하면요. 이 서브스페이스에서의 어떤 베이시스 벡터가 저기 직각인 베이시스 벡터 이렇게 있었다고 쳐봐요. 그러니까 요거 두 개가 이렇게 수직이에요. 그러면 요 벡터는요, 요 라인에다가 요거를 이렇게 수직으로 내려요. 그게 한 요쯤 됐다고 치고, 요 벡터를 요 라인에다가 이게 항상 그림이 어려워서 그러는데 이렇게 한 수직으로 이렇게 내렸다고 쳐봐요. 그럼 요 두 개의 벡터의 합으로 이 벡터가 나타나요. 그러니까 결국은 우리가 갖고 있는 이게 서브스페이스여서 이 라인을 어떻게 찾지? 이거를 굳이 걱정할 필요가 없이 얘 서브스페이스의 각각의 이 베이시스들에다가 그러니까 라인에다가만 결국 내린 다음에 그 컴포넌트를 합하면 그냥 요게 나오는 거예요.
그래서 이제
올소노멀이요? 네. 올소노멀, 그러니까 얘 벡터가 이제 길이가 1이면 이제 이게 내리는 게 좀 더 간단해지긴 하는데, 이거는 여기서는 이제 그거는 필요는 없어요. 올소노멀이 필요는 없어요. 이 프로젝션을 구하기 위해서.
서브스페이스의 차원에 따라서 그거를 사용을 더 많이 하는 거예요.
그러니까 결국은 베이시스 개수만큼으로 사용을 시킨 다음에 그걸 다 더한 거예요. 네.
시험을 5월 11일 날 두 번째 2차 고사를 본다고 들었어요.
네.
혹시 연기되나요?
50일이면 다음 주죠, 그죠? 연기 안 됐어요.
5월 11일 날 보는
네, 아마도.
블랙보드에 그 영상 두 개 보고 그 문제가
그렇게 해놨죠? 그러네요. 5월 11일 날. 그러면 아주 확실하진 않지만요. 한번 좀 상황을 좀 고려해보고요. 5월 11일이 아니고 다음 주 이제 화요일에 보는 거를 한번 생각을 해볼게요. 그걸 아마 오늘 내내 한번 공지를 내가 보겠습니다.
Can I take a picture for one slide, please?
Sure.
Because I couldn't for the null A and null A.
Okay.
Yeah. I name a new folder with mathematics.
Okay.
Math. Yeah.
Okay.
I have also one question, but the midterm will be 11?
Yeah,
I saw your email. You said
yeah, right.
you changed
So
it?
yeah, another student asked the same question. So I'm considering like a postponing to the next week's Tuesday.
Next week Tuesday?
Yeah, the following Tuesday. I mean, maybe it's like the Tuesday in the following week.
So it will be 13.
Not 13, I guess, because let's see. So this is Thursday, and so this 16th,
Oh,
which is the Tuesday in the following week.
that's very good. It's better actually. Okay.
Okay.
It's a bit cover chapter 6 also.
Yeah.
Please.
Otherwise you will have more loads towards the final. So
Okay. Oh, that's good. Yeah.
okay, see you.
Thank you very much.